Welcome back to Mastering A-Level AQA Physics. This guide will be covering the full section 3.8, which is nuclear physics, which is only covered on the A-level, not the AS. So let's begin with section 1, which is radioactivity. So section 1 includes, first of all, we have Rutherford scattering. So the content in this involves Rutherford's gold foil experiment, which was definitely pivotal in understanding the structure of the atom. So when alpha particles were directed at a thin gold foil, most passed through, but some were deflected, and they were deflected at large angles. We then have the qualitative study, which of course led to the discovery that atoms have small, dense nucleus, where most of the mass is concentrated, surrounded by empty space. So the impact of the nuclear model. This overturned the plum pudding model and led to the Rutherford model of the atom. So we've then got the opportunities for skills development. So definitely appreciate how scientific understanding evolves over time based on experimental evidence, and that's important because we can get asked questions based on the history of the atom model and radioactivity. So section 2 here, we've got alpha, beta and gamma radiation. So the properties, we've got alpha radiation, which consists of a helium nuclei. It has high ionizing power but low penetration, which is stopped by something like paper. We then have beta radiation, which consists of electrons or positrons, and it has a moderate ionizing power or penetration. It's stopped by something like aluminium, which is a bit thicker or denser. We then have gamma radiation, which is high energy photons, which has a low ionizing power, but it has a high penetration. It's reduced by lead or thick concrete. So, experimental identification. Use of absorption experiments to identify radiation types based on their penetration abilities. We've then got applications. We've got medical applications in terms of radioactive tracers and cancer treatment, such as PET scanners. We then have industrial. We have got thickness measurements of materials like aluminium foil. We then have ourselves the inverse square law for gamma radiation, which is the formula I equals K over R squared, where I is the intensity, K is a constant, and R is the distance from the source. We then have experimental verification. We can use a Geiger counter to measure intensity at various distances. Background radiation. Sources. Cosmic rays. We've got radon gas and medical procedures. Elimination from calculations. So to essentially eliminate the background radiation, we can just subtract the background count rate, which we measure before the experiment. We then have opportunities for skills development in this. We've got required practical 12, which investigates the inverse square law for gamma radiation. We've also got understanding the balance between the risks and benefits of radiation use in medicine and industry. We've then got section 2, which is radioactive decay. We've got section 1 of this, which is random nature of radioactive decay. So constant decay probability. So each nucleus has a constant probability of decaying per unit time. The decay equation is delta n over T equals minus lambda n, where n is the number of undecayed nuclei, lambda is their decay constant. Activity is therefore equal to lambda multiplied by n. So again, opportunities for skills development. We've got modelling decay using simultaneous equations like dice rolled, or using simultaneous or simulations like dice rolls to represent random decay processes. We've then got graphical analysis. We've got determining the half-life from decay curves and logarithm graphs. We've then got half-life, which is represented by t to the half, which is written as t and then a small half fraction written to the bottom right of it. So we've got the definition of half-life, which is the time taken for the nuclei to half in size. Or in other words, the time taken for half the nuclei in a sample to decay. The equation for half-life, or T to the half, is ln2 over our lambda, or decay constant. We've got applications of the half-life, which is radioactive dating, managing radioactive waste. We've also got opportunities for skills development here, which is determining half-life from graphical decay data, including decay curves and log graphs. We've also got, coming up next, nuclear instability. So we've got NZ graphs, which for stable nuclei, we plot the neutron number, N, against the proton number, Z, to identify stability. We've got several decay modes. We've got alpha decay, which will of course reduce both the N and the Z number by 2, because we have a helium nucleus which is 4-2. 2 protons, 2 neutrons. Beta minus decay, we'll have a neutron going to a proton, so we'll only increase the Z number by 1, the N number will remain the same. So, beta plus decay is of course the opposite, it decreases the Z number by 1, and electron capture will decrease the Z number by 1 also. We then have nuclear excited states. We have gamma emission of gamma rays from the excited nuclear states. Applications of this is the use of technetium-99 in medical diagnosis due to its gamma emission. Opportunities for skill development here too. We've got understanding and interpreting nuclear energy level diagrams. Similar to paper 1. We've then got coming up the nuclear radius. So we can discuss the nuclear radius and the estimation of it. So the closest approach of particles is using the Coulomb equation to estimate the nuclear radius, whereas with electron diffraction, we've got the nuclear radius through diffraction patterns. We've then got the typical values, which is familiarity with typical nuclear radii. We've then got dependence on nuclear number. So our equation for the nuclear radius is R equals R0 multiplied by a to the third, where R is the nuclear radius, R0 is a constant, and A is the nucleon number. So, constant nuclear density, evidence from the dependence of a radius on nuclear number. Opportunities for skills development here too. We've got making order of magnitude calculations for the radius of different atomic nuclei. We've then got section 5, which is mass and energy. We'll now explore the relationships between mass and energy in nuclear processes. Through Einstein's equation, the mass-energy equivalence equation, also known as E equals mc squared, where E is energy, m is mass, and c is of course the speed of light. We've also got binding energy, which is the energy required to separate a nucleus into its constituent protons and neutrons. We've also got the atomic mass unit, or U, which has a conversion factor of 1 atomic mass, which is equal to 931.5 mega electron volts. We've got calculations then, which can use mass differences to calculate the binding energy. Fission and fusion processes. Fission will split a heavy nucleus into lighter nuclei, whereas fusion will combine light nuclei to form a heavier nucleus. We've then got energy release, which calculating energy released in fission and fusion reactions. We've then got binding energy graph, which is where we can plot average binding energy per nucleon against nucleon number and identify regions where energy is released during fission and fusion. We've then of course got another opportunity for more skills development, which is appreciating how nuclear number or how nuclear physics informs decision making in energy production. We've then got induced fission, which fission can be induced by thermal neutrons. So we've got chain reactions, which essentially is a self-sustaining series of reactions, causing more interactions or reactions. We've then got critical mass, which is the minimum mass required to sustain a chain reaction. We've then got the nuclear reactor components. We have the moderator, which slows down neutrons to sustain the reaction. We then have control rods, which absorb neutrons to control the reaction rate. And we've got coolant, which removes heat from the reactor core. We've then got materials choices, and we've got factors such as considering properties like the neutron absorption and the thermal conductivity of those materials. We've then got examples of the materials used in reactors, such as graphite or water for moderators, and boron or cadmium for control rods. We then have another opportunity for skills development here, which is studying mechanical models of the moderation and elastic collisions. We've then got down here safety aspects, which is section 7. We've got fuel handling, so we've got remote handling, which minimises radiation exposures to workers, and we've also got shielding, which uses materials like lead to block radiation. We've also then got emergency procedures, such as shutdown systems, which mechanisms for rapidly stopping the reactor in an emergency. We've then got radioactive waste, which is the production and storage or self-handling and long-term storage solutions. We've then got risk-benefit analysis, which balances the benefits of nuclear power against the potential risks. We can then understand the societal implications of nuclear power. So that should cover all 7 sections of nuclear physics. Thank you for watching or listening, and see you in the next one. Thank you very much.